Welcome back. This is video number 3 for the UTSA EE3313, chapter 2.2.2. This is a video on the effects of the finite open loop gain. Okay, what does that mean? Okay, so let's see if we can develop this. Okay, first of all, in the last video, video number 2, we developed or derived this equation. This is for the inverting, since the signal is going into the inverting input. And this is the transfer function that you get. Now, there's a caveat to this. Okay, the caveat is that the open loop gain of the op-amp has to be high or large. Gain has to be very big. So as baseable gain goes high, this becomes real or becomes more accurate. Okay, so we're going to go ahead and try to derive an equation that shows that, and then we're going to see if we can model it, put some numbers, and see how the gain is affected, or actually how this equation is changed by the voltage gain. Okay, so first of all, keep in mind that the model of the op-amp, what's inside, you can model it as VD minus, okay, VD plus. Okay, so these are the input of the op-amp. Right? Looks something like this. And then the inside, there's actually a low voltage source. Looks like that. And that would be your V out. Okay. And the gain of this voltage is controlled by this open loop gain. Open loop gain. Okay. So if you have a voltage here and a voltage here, whatever the differential is multiplied times this eighth of a volt, and that will give you your voltage out. Okay. So basically you have that is equal to VD plus minus VD minus time eighth of a volt. Okay, so we're going to be using that equation. Okay. Okay, so keep that in mind. And I want to call this, I call this the op-amp model. This is the most simplest model that you can get to model a op-amp. As a matter of fact, you can use this model and put a capacitor and model or simulate bandwidth. Okay, so now what we're going to do is we're going to write the KCL at VD minus node. Okay, and then once we do that, we're going to solve for VD minus. Okay, so we'll go ahead and do that. So keep in mind that when we're deriving for this schematic or circuit. Okay, so VD node is supposed to be VD minus ES R1 plus VD minus out R2 equals 0. Okay, if you don't follow that, it's actually this node, and remember this is VD minus VD plus, at least that's what I'm calling it. So it's VD minus VS, that equation, divided by R1, okay, VD minus V out, VD minus V out, divided by R2, okay, so we have that, okay. So what I'm going to do is, let's see, I have it here in my notes, okay. I'm going to go ahead and expand this a little bit. VD minus 1, 2, okay, and we're going to bring DS 1, VDO R2, okay. So we expanded it out, and once you solve for VD, you should get VD minus equals R1 V out R2 yes, okay, R1 plus R2. Okay, so we have this equation. So I'll put a little star here. We're going to come back to that. See if I can add. Okay, so we got that. So now we're going to go ahead and get this equation. I'll put this equation, another star. I'm going to get this. I'll put it down here. Out. VD plus. VD minus. A sub O. Okay. Now, in the last lecture, we said we're assuming that the current going into the op-amp is 0. And if it's 0, that means that there's no voltage across, a drop across R3. Therefore, VD plus should be 0. And if that's the case, this is 0. Okay. So now what we do is we plug this into there. Okay. So that's the next strategy. V out R1, V out R2, ES R1 plus R2. Okay, so we got that equation, and now we have V out here, V out there, so we solve for V out. Okay, and there's quite a bit of algebra, but I'll leave the exercise for you. Okay, But if you do want the step by step, you can post a message on YouTube, and I will give me your email address, and I'll send you my notes. Okay, so once you let me see. Once you do the math, okay, you end up with V out, Vs, okay, is equal to negative R2 times the open loop gain divided by R1 plus R2 plus R1 some base of O. Okay, so here's the equation. Okay, but it's still not in the form that I would like for it to be, but just we're almost there. Okay, so let's see where we're at. So now what we can do is we can divide a sub O by both. So then we're going to get R2, and we're going to get R1 plus R1 R2 a sub O. Okay, so this is the final form that I wanted. Okay, so what does this tell you? Okay, well, if you notice, you have this term here. So let's assume if a sub O goes to infinity, if a sub O goes to infinity, which is in the denominator, then the entire this equation, or this, actually goes to 0. Okay, and if it goes to 0, okay, then all of this is just that. We're actually go ahead and move this. Is the original equation that that I derived in the second lecture. Okay, so this tells you that the higher this voltage or this gain is, the more you come closer to the ideal equation that we derived here. Okay, so let's see if we can simulate it and put some numbers, and we're going to use R sub 2 of 10k, R sub 1 of 10k as well. So we should have a gain of 1. And then let's try, see what the gain would be for a gain of 10. Gain of 100. Gain of say 10,000. And gain of 1 meg. Okay, we'll see how that does. Okay, how's it work? Okay, so what we can do is we can use Top Spice. Okay, Top Spice is the simulator that I use. You can actually download the demo and run these simulations. Okay, and I'll put the EE3313 Okay, and let me go back and just want to make a point that the SPICE model that I've been using, this model is actually a voltage control voltage source. That's what it is. So with that being said, there's a model here. I believe, let me look for it. I believe it's an E. Okay. I'm not sure if you can see it, but it says VCVS. This is actually a model or an op amp. It's actually a voltage source, and it's controlled by this voltage source. Okay. So what I'm going to do is, let's go ahead and mirror this if we can, or flip it. That way it looks a little bit more like the op amp. And we're going to go ahead and put a resistor here. Resistor here. And remember I said this resistor has to be half. Let me go ahead, change it around so it's consistent. So it'll be 10K, 10K, and it'd be 5K. Remember that that resistor has to be the parallel combination of these two. So we'll go ahead and put that there, that there. Okay, looks good. And the output, let me see how this is gonna work. Okay, that's gonna be the output. And let's see. Let me rotate this out. Okay, and we're gonna ground this there. Ground that there. There. Let's put a voltage input. Let's go ahead and put 1 volt. 1 volt there. Okay, the only thing that I'm a little concerned is that the positive is here and minus is here. Will that work? I think it will, except that I have to put it to flip the signs. I have to put, I believe, a negative number. Let me go ahead and put million just to see if it works. Okay, and let's see if we can do the operating point. Let's see if it flips the voltage. See if it inverts it. I got some kind of an error. Okay. See if it works. And it actually works. Okay, it says 1 volt there. Wonderful. Okay. So it works. Okay. So let's go ahead. Let's do some numbers here. Get the calculator. Okay. Go back here to the notes. Okay. Let's do the first one. Let's assume, let's calculate what the voltage would be if you have a gain of 10. Okay, so we know that it's 10k plus divided by 10k plus, so this would be 20k divided by, and we said a gain of 10. Okay, and we're going to put 1 volt. Okay, so this is going to be okay, plus, so it's 20k, so it'd be 2k. Okay, and we want, okay, let's see what we get there. So it should be -10 divided by 12. So it looks like the answer would be 0.833. So that's with an eighth of volt of 10. Now remember when we did 1 million, it was 1 volt. So let's see if it's true. See if we get the same. So what we do is we'll go here, change that 1 million, change it to 10. Simulation. Okay. And let's see what we get. What do you know? Negative 833.3 millivolts. Okay. In case you can't see it, there you go. So comes in agreement. We already did the 1 meg, and the 1 meg showed that you get 100. And in case you couldn't see it, let's go ahead and change the gain of this. And the reason, again, I'm putting a negative is because I'm flipping the voltage. Okay. So I'll put 9 again. So it's approaching ideal. With the larger the gain, the closer it gets to ideal. So now it should go back to 1 volt. So this proves that the equation does work, and I'll leave it up to you guys to plug in these numbers, and you'll see that this formula will predict the gain, and it shows you the effect basically that the higher the gain, the closer to ideal voltages you're going to get, or at least what you calculate. Thank you for watching. Bye.